In a world increasingly dependent on efficient and sustainable infrastructure, pipeline transportation remains a critical system for moving water, oil, and gas. However, traditional pipeline designs face persistent issues such as drag, material degradation, and energy inefficiency, especially in underwater environments, mostly. Our project explores how nature, particularly aquatic organisms like turtles and sharks, can inspire innovative pipeline solutions. So, by studying their survival mechanisms, we aim to enhance flow efficiency and reduce environmental impact, along with building resilient infrastructure. This, all coupled with the fact that we have multiple biological models and creations of technology that we did not have before when it comes to pipeline transportation, leads to a breakthrough that is, in all words, in all sense of the words, revolutionary. All right. Hi, everybody. It's Gabriel Stewart here doing the background for the slide for our TDP presentation. So today we're going to be talking about the background of pipeline transportation and its systems and what kind of problems we end up facing today. So pipeline systems are very essential for global transportation of liquids and gases. But the main issue is that we can't really use them underwater very well. See, they're limited by frictional drag and pressure damage depending on how deep you go. And leading to that pressure damage, it can cost you a lot of money, and I mean a lot of money, especially inside of the subsea environments. It gets really bad. So our current solutions that we have are attempting to address the issue. They're using synthetic materials and rigid designs to keep it, I think, steady and compact is their idea, but it's overall not going very well. So instead, we're trying to use a different approach for it. So instead of making it rigid, we instead implore biological models that we've observed in our environment by organisms that have managed to overcome this. So by looking at the natural models that have evolved to navigate water and the sea, like sharks and turtles and fish, we can design smarter pipelines. We'll get more into this later, but these types of pipelines can be used to redirect the flow of the sea currents or to move with it, have materials that are actually made to withstand the pressure using the models of organisms like sea turtles and their shells, and can also reduce the amount of drag that you have, which decreases the amount of energy that needs to be expended to actually create your model and design. It's very innovative stuff, and we'll be talking about it more in the next couple of slides.
Hi, my name is Daniel Ruiz, and I will be presenting the problem tree section on our final presentation. Sorry if the audio isn't the best. I'm currently filming this outside. So, looking at the problem tree that we're supposed to fill out, we have a core problem of whatever we're researching, and below that are primary causes for the problem and secondary causes, and above are the primary effects of it and the secondary effects. So, when we filled this out, we chose that the most important core problem was pipelines transportation causing environmental damage to areas. The three main causes of this that we went with was corrosion over time, excavation damage, and equipment failure. So, looking more into these three causes, with corrosion over time, this happens when pipes come into contact with water and oxygen. And if they're not taken care of properly and have the proper maintenance, they corrode, which damages the pipes and its overall integrity. Another main cause is the excavation damage done to the pipes. This happens when damage to the external coating of the pipe is caused by either digging or plowing, which damages the protective coating, which causes leaks and bursts. And another one that we went with was equipment failure. Most of the times when companies make these pipes, they try and save money and don't have proper equipment and materials in these pipes. Because of this, it can get damaged very easily. And another reason for these damages can be by earthquakes or faulty welds and in the manufacturing. The two effects that we went with were the pipe's potential bursts and leaks, which causes contamination of whatever liquid they're transporting, and the economic loss of it. So, with potential leaks and bursts, there could be potential and leaking hazardous liquids from whatever they're transporting, which can get into natural habitats and just cause a negative effect on whatever area they're in. And again, same thing with economic loss. Most companies try and go the easy route and save money, and because of this, when leaks and bursts happen, repairing and replacing those damaged parts causes those companies extreme amount of money, and this all could have been avoided if there was just better equipment and maintenance. And yeah, that's it. Thank you, and I'll let my teammates finish the presentation.
Hello, my name is Gabriel Stewart, and I'm going to be doing the first bit of the bio-inspired process for the TDP report presentation. So first, we're going to be going over the biologize, which is where we take our problem that we're having in the engineering world, and then we translate it over to biological conditions and lingo and words. So our issue is that we need the drag in the pipeline transportation to be reduced when we're underwater, and we also need the efficiency of materials and other such things that just come with having an underwater transportation system with pipeline. So first, I'm thinking that we need to think on how underwater organisms reduce drag to move faster in water to escape predators. That's a very big part of being in the water is being able to move faster, and to do that, you have to reduce current drag. The other thing would be remembering how some organisms use the current, which is in and outside of water. Organisms do that either way to move around more efficiently and use less energy. So with this, it's not very complicated. It's how fast you can go and how far you can go with the least amount of energy expenditure so that you can create something that can go far with less cost and resources in the engineering world. And then, of course, when you discuss engineering and building anything, the materials is going to be very important. And so you need to think about the materials used for that. For the organism side, it's not very important since they're born with it for them, but it's still very crucial and integral to them living. So I would still count that as a part of something to consider, as well as the strategies that they employ as well to maintain that, to use it, or just overall in general are things that we need to think about and put them into perspective. And I'll talk about that in the next slide, which I'll get to. But those are the main problems that need to be identified, and that is how you translate them into biological words and lingo. So I will see you in the next slide coming. Hi, everyone. Gabriel Stewart is here doing the second part of my assignment, which is the abstract. So today we're actually going to be talking about the biological system and model that we're using and modeling our transportation system after to create the effect that we wanted to. So in this case, we actually went for the sea turtle, not the amphibious ones, the ones that are, well, they're technically both amphibious, but not the ones with like actual feet. These are the ones that are mainly in the big, deep ocean, the big ones, the ones we all know and love, the Nemo ones. So um, it has an amazing biological solution to the problem of pipeline transportation. We need to reduce drag. That's perfect. If you can see on our graphs and sources that we have, the currents actually go over them due to the shape of their shell and the material of said shell with its grooves, which is really great for overall pipeline transportation if we can angle it as such. I mean, we can when we use it, so it would just be doing a workaround for the, not even the aerodynamics. They have that down. So really, the only thing we need to implement is the feasibility of how it can be built and maintained. But that might also be fixed in the actual creation of the shell material, which we can also model after the turtle, as it's good, tested, tried, and true. One of the other things that's very important are the strategies that they use to reduce drag when they're inside of an underwater current. So as we know, sea turtles like to ride the underwater currents. We all saw it in Nemo. We know they do that. It's obviously not that exaggerated, but it is something that they do, where they go into the current, and as they're going, we need to make sure that the wind goes over them and doesn't obstruct and hit them full on. If it does, then that's going to induce drag, and that's going to reduce their speed, which can be very bad when it comes to escaping from predators, transferring around, and just overall energy efficiency. It's never really good. So that's another one of the things that we can super improve on if we use their model of moving in their way of their materials and the type of shell that they have, all shown right here. Another thing that I haven't added that I think would be very impressive, I know it might be talked about later on, that isn't necessarily part of talking about the turtle is that if we were to employ some type of hydrophobic material, it would decrease the amount of drag that's experienced exponentially anyway, because the water would slide off of it along with the overall current itself. So that's basically all I have here, but hopefully the other ones are great too. I'm sure my teammates will do a great job. So I'm excited to have the next bit of this slide go through. So thank you so much for staying here, and I'll see you in the long run.
Now we move into the discover phase, where we look at natural models that solve similar problems to pipeline drag and pressure underwater. We identified four key inspirations: turtle shell microstructures, which naturally reduce drag in the water and can resist high pressures; turtle behavior, where turtles reorient themselves with water currents to minimize the amount of energy they use; shark skin, which has riblet patterns that reduce drag and prevent organisms from attaching, a process called biofouling; and fish scales, which overlap like flexible armor, offering both strength and flexibility under pressure. Each of these organisms also have survival strategies that align with our goals. Turtles use textured shells and hydrophobic coatings to survive strong currents. They also reposition with the flow of water to conserve energy. Sharks move efficiently while also self-cleaning, and fish maintain their mobility and protection through the flexible scaling of their skin. These natural strategies give us a strong foundation for designing a more efficient and resilient underwater pipeline system. Building on what we discovered, the emulant phase focused on translating these natural strategies into engineering solutions. We propose using a micro-textured lining inside the pipeline, inspired by turtle shells, to help guide the flow of water and reduce friction. We're also introducing adapted flow baffles, thin structures that can slightly rotate with water pressure, similar to how turtles adjust their bodies to currents to save energy. To prevent buildup and reduce drag even further, we suggest a hydrophobic coating inspired by shark skin. Finally, the pipeline walls would be layered. The outer layer would be tough but flexible like creatine for impact resistance. The inner layer would mimic the strength and layering of of bone to handle internal pressure. When we evaluate this design, the estimated manufacturing energy is between 100,000 and 300,000 megajoules, but in return, it would greatly reduce maintenance and repair needs. Some challenges include the initial cost and reliance on plastics or silicone, meaning we need early stage investor funding. To improve, we recommend using recyclable or bio-based materials in future versions, making pipeline modular and upgradable, and allowing for passive adaptive feedback over time. For overall, the design follows many of the life principles. It adapts to changing conditions using life-friendly chemistry, minimizing maintenance, responds to local flow conditions, although we still need to work on long-term sustainability and evolution compactability. And on the side, it shows our what would be our pipeline and how we would incorporate the turtle shell, and then the how we would have it layered.